Hi everyone, I'm Yang Chen from Tianjin University. It's my pleasure to share our work on unit testing here. Software testing plays a critical role in software development, ensuring that software behaves as expected and is free of defects. Unit testing is a cornerstone of this process. It helps catch defects early, reducing both the cost and effort required to fix them later. For these reasons, unit testing is important in software development. Automated unit testing has evolved from traditional automated tools to large language models based approaches. Traditional search-based techniques such as the well-known tools AlphaSuite and Rundup rely on randomly generated inputs and search algorithms to produce test cases. With the advance of large language models, recent research has begun to leverage their powerful capabilities in code understanding and generation to automatically generate unit tests. There are two main ways to leverage large language models. The first is to train a model on large-size code corpora, and the second is to prompt an existing model through in-context learning, often incorporating example cases as guidance. Since training a model from scratch requires significant computational and time resources, we focus on the lightweight and flexible FL-based approach. Some prior studies have explored incorporating in-context examples to improve generation quality. For instance, RegGen retrieves similar examples from human-written test suites, while Telpa retrieves ineffective counterexamples from automatically generated tests. However, the examples used in these techniques often suffer from limited semantic clarity. First, they may involve complex logic spanning multiple test scenarios within a single test. Second, they often exhibit insufficient textual clarity, such as ambiguous identifier names or missing comments. Such limitations in semantic clarity ultimately undermine the effectiveness of these SAO-based techniques. To address this issue, UTGen made an initial attempt. Leveraging the strong code comprehension capabilities of large language models, it uses LLMs to refine existing tests, generating new ones with better data quality, clearer comments, and more meaningful naming. However, the complex logic of unit tests still poses significant challenges for LLMs in accurately understanding the test's semantics. Furthermore, hallucination issues may undermine the original test's functionality or even produce invalid test cases. To handle those challenges, it's a natural idea to purifying the tests to transform complex tests to simpler ones and combines both LLMs and program analysis to avoid errors caused by hallucinations. Based on these insights, we propose CLAST, which consists of two main components. The first is test purification, which transforms complex tests into simpler, semantically coherent ones. The second is textual clarity refinement, which ensures correctness by incorporating program analysis while enhancing textual clarity. Given an original test as input, CLAST produces a set of refined tests with improved semantic clarity. To perform test purification, CLAST first applies what we call statement optimization. This step prevents syntax errors or accidental deletions when simplifying code later. It breaks down compound statements into smaller atomic ones. For example, if a statement declares multiple variables or uses chained assignments, CLAST splits them into individual simple statements. Other parts, like method call chains, are left unchanged to keep the code correct. We also treat control structures, such as for loops or if statements, as a single unit, so we don't end up removing only part of them. Overall, this conservative approach keeps the test valid while making it easier to simplify. Next, a single test often contains multiple assertions, each checking a different scenario. To improve clarity, CLAST splits such tests into multiple smaller ones, each with only one assertion, and then removes unrelated statements. It does this using data flow analysis to track dependencies between variables and statements, and applies backward slicing from each assertion to keep only the relevant code. To avoid redundancy, CLAST merges tests with the same setup by combining their shared prefix and all related assertions. After this step, we get a set of purified tests that are simpler and more focused. Next, since many studies highlight the importance of clear comments and meaningful identifiers for better semantic clarity, CLAST performs textual clarity refinement. For comments, CLAST uses one-shot prompting with LM to generate clear explanatory comments and then insert them into the purified tests. It uses semantic similarity to decide the most appropriate places for these comments based on the abstract syntax tree. For identifiers, CLAST first traverses the abstract syntax tree to collect all variable declarations and their usages. Then it again applies one-shot prompting to suggest improved identifier names and replaces them in the original test code. In this way, CLAST preserves the correctness of the original tests while enhancing their textual clarity. To evaluate CLAST, we compared it with UTGene and on 4 Defects4J projects and 3 internal Huawei projects. We focused on 2 aspects. First, to ensure the refinement doesn't harm test capability, we measured line coverage, compilation success rate, pass rate, and mutation score. Second, we conducted a user study to assess the semantic clarity. In the study, 15 experienced Java developers, 10 from industry and 5 from academia, averaging 6.8 years of experience, were asked to rank the original and refined tests based on 3 criteria. The first is conciseness, representing the clarity of test scenarios. The second one is descriptiveness, representing the quality of identifiers. And the third one is comment quality, representing the clarity of comments. For Q1, we evaluated CLAS's effectiveness in refining tests while preserving their original capability. We sampled 500 developer-written and 500 tool-generated tests to balance generalizability and cost. CLAST demonstrated a strong ability to preserve test effectiveness while significantly improving semantic clarity compared to UTGene. Specifically, CLAST fully retained the original test effectiveness, whereas UTGene reduced compilation success rate, pass rate, coverage, and mutation score by 12%, 35%, 4%, and 5% on average. In the user study, where a lower rank indicates better clarity, over 85% of participants prefer the tests refined by CLAST in terms of conciseness, descriptiveness, and comment quality. These results confirm that CLAST effectively enhances semantic clarity and comprehension without sacrificing correctness. For Q2, we examined whether CLAST refined tests can further enhance ICL-based unit test generation. We now incorporated 3 types of in-context examples, including original, UTGene refined, and CLAST refined into RecGene and TELPA. Using CLAST refined examples consistently improved generation quality, achieving average gains of 10%, 13%, 20% in compilation success rate, pass rate, and coverage, and up to 25%, 28%, and 45% over UTGene refined examples. These results confirm that high semantic clarity examples from CLAST provide guidance for LLMs, leading to more accurate and effective test generation. For the ablation study, we removed the key components of CLAST, test purification and textual clarity refinement, to see how each affects performance. When we removed post-processing, test effectiveness dropped noticeably. And removing both purification and post-processing caused even larger drops. And the user study also confirmed that both components are important for improving the clarity of refined tests. When used as in-context examples, tests refined by CLAST still outperform all other variants, confirming that both components contribute to the overall effectiveness. To conclude, we developed CLAST, an innovative refinement technique that enhances the quality of unit test examples by splitting a complex test into a set of purified ones and improving their textual clarity using combination of LLMs and program analysis. Our evaluation and real-world projects demonstrate its effectiveness. That's all my presentation. Thank you for your attention.